So basically, we have this DS2MA dataset. So our main goal is to pre-process the data, and it contains various SNR ratios from the radio receivers. It ranges from minus 17 dB to minus 25 dB, and there are only two types of signals in here, namely Gaussian and impulsive. So first, we have to split the data into real and imaginary parts. Okay, then after we have to shuffle it and normalize it, like we have plotted all the data here, and we have to first normalize it and then take the complex integrate from here. Okay, then we have merged it over here, and after that we have used the scikit-learn library to train trace split the data. And here we have this, the two indicates here real and imaginary part. Okay, then we have used the keras tuner library, which basically gets the best parameters we could get, like here, which could be used further for using in our designing our architecture. Okay, so here's our architecture here with all the trainable parameters here and the size. Then here's the training with here we have used 20 epochs. Then here's all the weights which are being saved here layer wise. And here's the plot of our graph, the plot of accuracy and loss. Then here's the heat map, which contains the confusion matrix. That is the what is our prediction? This is the true positive, true negative, false positive, or false negative.
Okay, now I'll move forward with the presentation for the hardware side. Okay, sorry, yeah, soft console is pending. Okay. Soft console.
Just in the soft console side.
Okay. So here we have this soft console project which shows the C++ implementation for the dense layers. Here we have included the an example flattened output from the convolutional layers as a header file. Since the header files are quite large, we have included it in a separate section in the linker file and not in the L2lim section, by creating a pointer in the header file and then pointing it to a separate CPP file which contains the actual data, and while the text section or the code section is stored in the L2lim section, the header files themselves are stored in the DDR non-cached 32-bit section. So if we'll just scroll down a bit, so here we have defined the primitive functions for the dense layers, the ReLU and sigmoid activation functions, and the dense layer function. The dense layer portion of our CNN contains just two layers. So we have a layer 1 and layer 2 in the defined in the void E51 function. Okay, yeah. So here we have first defined some constants by extracting the values from the stored header files which contain the flattened output as well as the weights for the for both the layers and the biases. And then we have implemented the two dense layers and then printed the final output from the cout. So while we faced some errors in building this file initially because of the size constraints in the L2lim section, which were then solved by moving those sections to the DDR section, we are still facing problems in while the build compiles without errors and it builds without errors. We are facing issues in actually running this on hardware. In our case, it reaches 100, starts launching, and then reaches 100% progress on configuring GDB, but then it gets stuck there. So now I'll move on to the hardware section. I'll present my screen. Okay. So here is the hardware project in Libero. I'll first start with the This is the our overall top module. I'll start with the top control module. The top control module actually manages all the modules inside the top module, which contain the address generator for the data and the weight buffers, the control buffer as well as the bias buffer. Then we have uh, yes, the data address generator. This module takes inputs from the control buffer about the input image size, the padding which is required, and the stride which is required, and then generates the output addresses for the buffers. This is the register file. This takes serial input from the data buffers and then generates then collects 9 data inputs and then supplies them concurrently to the MAC unit. This is the MAC core. This performs the 3x3 convolution operation, and this here is the max pooling module, which performs the 3x3 pooling operation. For average pooling, we again use the MAC core and supply 1/9 as the weights. On the final layer, on the final input channel of any current, the MAC unit also handles adding the bias to the output, and then the final output is saved to the output buffer. And then for the next layer, the output buffer is then cycled into switched to the input buffer. So there are basically two symmetrical buffers which take turns acting as the input and output for the design. Thank you.